Today I am going to talk about continuity of a function. Continuity of a function help us to understand many engineering and scientific applications. In our day-to-day life, we draw two types of graphs. One is by lifting the pen of the paper, another without lifting the pen of the paper. Let us see the following graph. Let us see how the following graph is drawn. The following graph is drawn without lifting the pen of the paper. See once again. Let us see the another graph. This graph cannot be drawn without lifting the pen because there is a certain part is broken. There is a certain gap where the graph is not present. So to draw this graph, we required to lift the pen of the paper, then only we can complete the graph. From this, it is clear that some graphs can be drawn without lifting the pencil and some other graphs can be drawn only by lifting the pencil of the paper. This way of drawing the graphs is going to help us to decide continuity and discontinuity of a function up to certain extent. Till now, I was talking about continuity of the function on the basis of sketching the graph. If we are able to sketch the graph without lifting the hand of the paper, then it is continuous, and we are lifting the hand, then it is discontinuous. But that is not a complete idea. To decide continuity of a graph or a function, we need to know more about it. There are more hidden formulae, hidden ideas which help us to decide continuity of a function. So these theorems and these statements I am going to teach you now to decide continuity and discontinuity of a given function in a given interval at a given point. The concept of continuity depends upon whether the limit exists and limit does not exist. This is the key idea to decide continuity of a function. To understand the words limit exists and limit does not exist, to understand this, let us look at some examples. Rule for limit to exist is left hand limit value and right hand limit value must be equal. That is, limit x tending to c minus f of x is equals to limit x tending to c plus f of x. If this condition is satisfied, then only limit of given function exists, otherwise it does not exist. Show that limit x tending to 0, 1 upon x does not exist. For that, we first write y equals to 1 upon x, and we shall be drawing the graph of y equals to 1 upon x. Now y equals to x raised to 0 upon x raised to 1. 1 can be written as x raised to 0, and here is a 0 is there, so that is a top index equals to 0, and here x is equal to 1, that is a bottom index equals to 1. Here top index is smaller than bottom index, therefore asymptote is y equals to 0. Similarly, given equation can be written as x equals to 1 upon y. Here the same case, the top index is smaller than bottom index. Here is x equals to 0 is a asymptote. Thus y equals to 0 is one asymptote and x equals to 0 is another asymptote. Now we are having y equals to 1 upon x. From this we get 4 cases. One is y equals to minus infinity, y equals to plus infinity, and x equals to 0. Here also x equals to 0. This is a case 1, case 2, and case 3. We get here x equals to minus infinity when y equals to 0, and x equals to plus infinity when y equals to 0. We are having y equals to 1 upon x. So let us prepare a table. In this table, let us take the various values of x and y. If I take x equals to 0, y equals to infinity, and here I am going to take x equals to 1 plus 1, then y equals to 1. But after the 1, if I take 2, the value of y will keep on decreasing. Y value has become 0.5, and if I take 3, y value 0.33, and if I take 4, 5, 6, then y values are 0.25, 0.2, and 0.1. Now by using these values, we shall draw the graph. As x increases, y decreases. Similarly, for negative values of x, the graph shape like this. And asymptotes, the x-axis is the asymptote. This is the x-axis. This is the asymptote, and y-axis also asymptote. Now come back to the problem. We had the graph. The y-axis was asymptote and x-axis was asymptote, and the shape of the graph was like this. Now here one thing I want to clear. Asymptotes are nothing but the tangent to the curve at infinity. Now we will finding left hand limit and right hand limit. So limit extending to 0 plus f of x equals to limit extending to 0 plus. What is f of x? F of x is nothing but given problem, that is y equals to 1 upon x. So the 1 upon x is nothing but f of x, and this becomes plus infinity, and limit extending to 0 minus f of x equals to limit extending to 0 minus 1 upon x. This becomes minus infinity. From this we get limit extending to 0 plus f of x not equal to limit extending to 0 minus f of x. Since right hand side limit and left hand side limit are not equal, therefore limit does not exist at x equals to 0. Now suppose I want to trace the graph by using pen. So I am able to trace here with the red color, you can see. But to continue draw the other part of the graph, I need to lift my pen, then only I am able to draw the graph. This is happening at x equals to 0. Therefore we can say the graph is not continuous at x equals to 0. From above discussion we can learn two things. One is that left hand limit value not equal to right hand limit value, that is limit extending to 0 plus f of x not equal to limit extending to 0 minus f of x. That means limit does not exist. Since limit does not exist at x equals to 0. Therefore, function is not continuous. Function is not continuous at x equals to 0. Test for existence of limit of if I equals to limit extending to 0 e raised to 1 upon e raised to 1 upon x minus 1. Now I am going to test whether the limit exists or does not exist. Now we will divide the problem into two parts. One is limit extending to 0 plus e raised to 1 upon x divided by e raised to 1 upon x minus 1, and second part of the problem, limit extending to 0 minus e raised to 1 upon x and e raised to 1 upon x minus 1. Now we shall be finding out right hand limit and left hand limit and see that what is their results. Simplified as limit extending to 0 plus 1 upon e raised to 1 upon x divided by e raised to 1 upon x minus 1 upon e raised to 1 upon x. Limit extending to 0 plus 1 upon this and this cut down 1 minus 1 upon e raised to 1 upon x. We know that limit extending to 0 e raised to 1 upon x equals to infinity. Therefore, limit extending to 0 plus 1 upon 1 minus 1 upon infinity equals to limit extending to 0 plus 1 upon 1 minus 0, because 1 upon infinity equals to 0, that is equals to 1 upon 1 equals to 1. Therefore, limit extending to 0 plus f of x equals to 1. Now we know that limit extending to 0 minus e raised to 1 upon x equals to 0. Therefore, limit extending to 0 minus e raised to 1 upon x minus 1 equals to 0 upon 0 upon minus 1, 0 upon minus 1. Therefore, limit extend to 0 minus f of x equals to 0. Now there is a rule. What is the rule? If left hand limit not equal to right hand limit, then limit does not exist. This is rule. Since in our problem the left hand value equals to 0 and right hand side value equals to 1, and therefore the limit does not exist at x equals to 0. 0 can't be the limit of this function because both the values are different. Thus, rule for limit to exist is left hand limit value and right hand limit value must be equal. That is, limit x tending to c minus f of x is equals to limit x tending to c plus f of x. If this condition is satisfied, then only limit of given function exists, otherwise it does not exist. Definition of limit of a function at c. Now we are going to define the limit of function at c by using epsilon and delta concept. Let set A is a subset of R and C be the cluster point of A. Then for the function A to R, there is a real number L is said to be limit of the function f if x minus c greater than minus delta and x minus c smaller than plus delta, and f of x greater than L minus epsilon and smaller than L plus epsilon. Then we say limit exists at x equals to c and limit value equals to L. Now let us understand the meaning of epsilon, delta and L with the help of following graph. The graph is drawn and a vertical line drawn at cluster point and corresponding value on y-axis, that is equals to L. We are going to talk about L. What is L? L is the limit of the function. We drawn a green line at a distance of delta away from the line at cluster point. The distance between the blue and the green line is equals to delta. We drawn again another line left side to the C at a distance of delta. Coordinates at the right side and the left side of C becomes C plus delta and C minus delta. The distance between the blue and the violet line on y-axis is equals to epsilon, and the red and blue is equals to epsilon, and L is the middle of L plus epsilon and L minus epsilon. Let us draw a line near to the cluster point. Let x be the coordinate of the black line and corresponding value of the function on y-axis, that is equals to f of x. This distance is epsilon and this distance between the two lines is delta. Epsilon is distance between the two lines, therefore epsilon is greater than 0. Delta is also distance between the two lines, therefore delta is also greater than 0. Implies for every epsilon there is delta. Now it is clear how the diagram has been produced. Diagram for y equals to f of x been drawn and delta is decided on the x-axis and epsilon is decided on y-axis, and we can define the limit of the function. The limit of the function can only be defined if you know the delta value. If you don't know the delta value, you cannot define limit of the function. Once you know the delta value, then you will also come to know what is epsilon value. That means once you get the delta point, you will get the epsilon value. Delta can be known only when you know the cluster point. That means cluster point is important to get the knowledge of delta, and epsilon can be known only when you know the delta. Once you decide epsilon value and delta value, you can define the limit of the function. That means they are all interrelated with one another. That means for given delta value, we can easily find out epsilon value. Once you get the delta value and epsilon value, you can easily find out limit of the function. Limit of the function L is such that f of x must be greater than L minus epsilon and must be smaller than L plus epsilon. Thus, the limit of the function at C can be defined. Conditions for a function to be continuous. There are the few conditions. If we satisfy, then only a given function is continuous. The first condition is that we must be able to define a function. If we are not able to define a function at x equals to a, then it is not continuous at x equals to a. Second one, limit exists. If the limit exists, then only the function is continuous. If the limit does not exist, then the function is not continuous. We have seen the meaning of limit exists in our previous discussion. And the third important condition, the left hand limit must be equal to right hand limit. And the last one, limit extending to a f of x must be equal to f of a. These are the few conditions, these are the few primary conditions for the function to be continuous. Let set A is a subset of R and let C be the cluster point of A. Then for the function A to R, let us consider the two functions f and g which are continuous at C. C is the cluster point and point C belongs to the set A. Then combination of functions f and g is also a continuous function, that is f plus g is also a continuous function. Similarly, difference of f and g is also a continuous function, that is f minus g is also a continuous function. Let k belongs to R, then kf and kg also continuous functions. That means f and g are continuous, and if you multiply them by suitable number, then resulting functions also continuous at C belongs to A. The product of functions f and g also a continuous function. The division of f and g is also a continuous function. That means f divided by g is nothing but a continuous function if only if f and g are continuous. From above, it is clear that f plus g, f minus g, k into f, f into g and f upon g, all these functions are continuous functions at C. C is a cluster point of given set A. If z of x equals to f of x plus g of x, and if f of x is continuous function and g of x is also a continuous function, then z of x, which is nothing but combination of two continuous function, is also a continuous function. Let us understand this by taking one example. Let z of x equals to sin x plus cos x. Let f of x equals to sin x and g of x equals to cos x. Thus z of x equals to f of x plus g of x. F of x equals to sin x. Sin x is continuous function for all values of x. Similarly, cos x, that is g of x equals to cos x, is also continuous function for all values of x. Thus, z of x is a combination of f of x and g of x. F of x is continuous function and g of x is also continuous function. That means z of x is addition of two continuous functions. Addition of two continuous functions. So as per as the rule, the addition of two continuous function is also continuous. Therefore, z of x is continuous function. From this example, it is clear whenever you got the two continuous function at a particular value of x, their addition is also a continuous function. If z of x equals to sin x multiplied to cos x, is z of x is continuous function. Let f of x equals to sin x and g of x equals to cos x. Therefore, z of x equals to f of x multiplied to g of x. Since f of x equals to sin x, that is continuous function for all values of x. G of x equals to cos x, that is also nothing but a continuous function for all values of x. Therefore, z of x is product of two continuous functions. Product of two continuous functions. Since z of x equals to sin x multiplied to cos x, multiplying and dividing by 2, so 1 by 2, 2 sin x and cos x equals to 1 upon 2 sin 2x. So z of x equals to 1 upon 2 sin 2x. Since we know that sin 2x is also a continuous function for all values of x. Therefore, z of x equals to continuous function. Implies product of two continuous functions is also a continuous function. Hence proved. If z of x equals to x raised to 4 plus 1 upon x cube plus 1, is z of x continuous? Question mark. Let p of x equals to x raised to 4 plus 1 and q of x equals to x cube plus 1. Therefore, z of x equals to p of x upon q of x. P of x is a polynomial and q of x is also a polynomial. Since polynomial function is continuous at every point on R, therefore p of x is continuous on R and q of x is continuous on R. Both polynomials are continuous on R. Therefore, resulting function of p of x upon q of x is also a continuous function. Implies z of x is continuous. let us consider a theorem of continuity of composite function GOF. Under this, I am taking the two sets, set A and set B. Both the sets are belonging to R. Now we consider the two functions f and g, the function f a to r and the function g b to r, and we also relate the function f and g by using the function of a is a subset of b. Let f is continuous at a and g is continuous at b and g of a equals to b. Then the theorem says GOF a to r is also a continuous function at a. Let us prove the theorem now. Consider a set of real numbers R. Consider set A under the set of real numbers R. Consider set B, which is also under the set of real numbers R. Implies set A and set B are subset of set of real numbers R, and A and B are related by relation f of A is a subset of B. The entire theorem is based upon the sets A and set B. For better understanding, let us consider D, E, F elements present in set A and P, Q, T, these elements are present in set B. As per as the given information, f of A is a subset of set B. So, f of D equals to P, f of E equals to Q, and f of F equals to T. That means from set A we get the subset of set B. F of A is a subset of set B. So P, Q, T are the elements which are present in the subset of set B. Now we'll try to understand this theorem by using the following graph. The graph is corresponding to y is equal to f of x, and we got a point A on x-axis and point B on y-axis. We have to talk about continuity of the function at point A, and the graph is corresponding to y is equal to f of x and f of A equals to b. B is drawn on y-axis. We took a vertical line nearby A and corresponding value on y-axis, that is y. For x there is a y, x value on the x-axis and the corresponding value on y-axis, and we got the eta here, and left and right side of A we got A minus delta and A plus delta. A is as good as a cluster point, and we got delta here, and x minus A, magnitude of x minus A less than delta, it is clear from diagram, and magnitude of y minus B is less than eta. So we have defined here two things: magnitude of x minus A less than delta, and magnitude of y minus B is a eta. From given information, G of A equals to B, and F is continuous at x equals to A. from graph, here is a and here is a B, implies f of A equals to B. Also, G is continuous. G is continuous at G of A equals to B. From figure, y minus b less than eta implies G of y minus G of b less than epsilon. Let us call it as equation number 1. Also, from figure, x minus a less than delta implies f of x minus f of a modulus of f of x minus f of a less than eta. Let us call it as equation number 2. Since modulus of y minus b less than eta and modulus of f of x minus f of a less than eta implies these two equations are almost similar. From these two equations we get another information. Since modulus of y minus b less than eta, modulus of y minus b less than eta provides modulus of g of y minus g of b less than epsilon. Since y equals to f of x and b equals to f of a, we have modulus of g of y minus g of b less than epsilon implies in place of y I can write f of x minus in place of b I can write f of a less than epsilon. Therefore, for modulus of x minus a less than delta, we have modulus of g of f of x minus g of f of a less than epsilon, which can be written as GOF of x minus GOF of a modulus of GOF of x minus GOF of a less than epsilon. That is, for modulus of x minus a less than delta, we have GOF of x. GOF nothing but g of f of x. GOF of a less than epsilon. Here epsilon delta criteria is satisfied. Therefore, on the basis of epsilon delta criteria, the theorem is proved. That is by definition, by given condition, GOF is continuous function at x equals to a. Hence proved. If function a to r and if f is continuous at x equals to c, then modulus of f is also continuous at x equals to c. We can prove this theorem by using epsilon delta concept. Let C be the cluster point. Let x be any point around cluster point. We are having epsilon. Epsilon is nothing but distance between the two lines. Therefore, epsilon greater than 0. When epsilon is greater than 0, then corresponding value of delta, this is delta. Delta is again the distance between the two lines. So, delta is also greater than 0. Thus, we have epsilon and we have the delta. And f is continuous at x equals to c. Now, we observe that the x and c, the distance between x and c is smaller than delta. This is x and this is c, and here it is c minus delta. So this distance is delta. So of course the distance between x and c is smaller than delta. So that is nothing but x minus c. So x minus c, the modulus, the positive distance, because distance is always positive. So the modulus of x minus c less than delta. That is the purpose of taking the modulus, that because the physical distance is always positive and modulus of x minus c is smaller than delta value, implies f of x minus f of c. The modulus of f of x minus f of c will be smaller than epsilon value. Now we know that the modulus of f of x minus f of c, this will be greater than the, if you take the f of x modulus and f of c modulus and again the entire modulus. Suppose we take the modulus like this, modulus inside the modulus like this, then it would be smaller than epsilon. That will be less than epsilon. Implies if modulus of x minus c smaller than delta, then modulus of f of x minus modulus of f of c will be smaller than epsilon. Implies modulus of f is smaller than epsilon. Implies f is continuous. Then modulus of f also continuous at x equals to c. Hence we proved the theorem. If function a to r, let f of x greater than or equal to 0 for all x belongs to a, if x is continuous function at x equals to c, then root f is also a continuous function at x equals to c. That we need to prove. And primary condition for a continuous function, nothing but limit extending to c f of x equals to f of c, and the second condition, limit extending to c f of x, the limit must exist. If these two primary conditions are satisfied, then given function is continuous. And here is a f of x is already continuous function. Therefore, limit extending to c f of x already exists because it is already a continuous function. Now we take limit for limit extending to c root of f of x, that is equals to under root of limit extending to c f of x, that is equals to root of f of c. If limit exists at x equals to c, then f of x minus f of c is smaller than epsilon. Now taking root both side, modulus of f of x minus f of c is smaller than root epsilon, and modulus of f of x minus f of c will be very much smaller than epsilon, implies root f is continuous at x equals to c on the basis of epsilon delta criteria. Therefore, if f is continuous, then root f is also continuous function. Discuss the continuity of the function f of x, where f of x equals to 2x plus 3 if x is less than or equal to 1, x square plus 4 if x is greater than 1 and less than 2, 3x plus 2 if x is greater than or equal to 2, less than 4, and 4x minus 2 if x is greater than 4 and less than 5. Now we can test the continuity at x equals to 1 because x smaller than x greater than information given to us. We can test the continuity at x equals to 2 because x smaller than 2 and x greater than 2, both the functions are provided to us. Similarly, we can test the continuity at x equals to 4 because f of x less than 4, f of x greater than 4, both informations are given to us. Now testing continuity of the function at x equals to 1. For x less than or equal to 1, f of x equals to 2x plus 3. Therefore, limit x tending to 1 minus f of x equals to limit x tending to 1 minus 2x plus 3 equals to 2 into 1 plus 3 equals to 5. Similarly, for x greater than 1, f of x equals to x square plus 4. Therefore, limit x tending to 1 plus f of x equals to limit x tending to 1 plus x square plus 4 equals to 1 square plus 4, 1 plus 4 equals to 5. Limit x tending to 1 minus f of x equals to limit x tending to 1 plus f of x. Both results are equals to 5. Both results are equal, that is equals to 5. Implies f of x is continuous at x equals to 1. Now testing the continuity of the function at x equals to 2. F of x equals to x square plus 4 for x less than 2. Therefore, limit x tends to 2 minus f of x equals to limit x tending to 2 minus x square plus 4 equals to 2 square plus 4 equals to 8. Similarly, limit x tending to 2 plus f of x. This is nothing but f of x for x greater than 2. Limit x tending 2 plus 3x plus 2 equal to 6 plus 2 equals to 8 implies limit x tending to 2 minus f of x equals to limit x tending to 2 plus f of x implies f of x is continuous at x equals to 2. Now testing the function at x equals to 4. F of x equals to 3x plus 2 for x less than 4. Therefore, limit x tending to 4 minus f of x equals to limit x tending to 4 minus 3x plus 2 equals to 3 into 4 plus 2, 12, 14, and limit x tending to 4 plus f of x equals to limit x tending to 4 plus 4x minus 2 equals to 4 into 4 minus 2, 16 minus 2 equals to 14 implies limit x tending to 4 minus f of x equals to limit x tending to 4 plus f of x implies f of x is continuous at x equals to 4. Therefore, f of x is continuous function at x equals to 1, x equals to 2, and x equals to 4. Continuity of a composite function. If a function is continuous at x equals to a and g is continuous at x equals to f of a, then the composite function g of f of x is continuous at x equals to a. On the basis of this, let us consider one example. If f of x equals to sin x, g of x is equal to x cube, where f of x and g of x are continuous for all values of x belongs to R, then prove that sin cube x is continuous function. Solution. Here we shall be finding out composite function of g, that is g of, that is g of f of x equals to g of sin x equals to question mark. Since g of x equals to x cube, therefore g of sin x equals to sin x whole cube equals to sin cube x. Since f of x equals to sin x and g of x equals to x cube and their composite function, if f is a continuous, g is continuous, then composite function GOF is also continuous. GOF of x equals to sin cube x. Sin x is already continuous, x cube already continuous, Therefore, sin cube x is also a continuous function. Hence proved. Show that the absolute function f of x equals to modulus x is continuous at every point c belongs to R. If f of x is continuous at x equals to c, then for every epsilon greater than 0, there exists delta greater than 0. Now draw x and corresponding f of x on y-axis. Now x minus c, modulus of x minus c smaller than delta, and modulus of x minus modulus of c less than epsilon. Call it as a equation number 2. From equation 1 and 2 we get modulus of modulus x minus modulus c less than or equal to modulus of x minus c. Let us call it equation number 3, where modulus x is nothing but f of x and modulus of c is nothing but f of c, implies modulus of f of x minus f of c less than epsilon, implies f of x equals to modulus x is continuous at every point c belongs to R. Hence f of x is equal to modulus x is a continuous function. Discuss the continuity of the function f of x at x equals to 0, where f of x equals to 2x plus modulus x upon x. This problem has to be done for left hand limit and right hand limit. For that we have to find out limit extending to 0 plus and limit extending to 0 minus. We know that limit extending to 0 plus modulus of x equals to plus x, and limit extending to 0 minus modulus x equals to minus x. These two properties I am going to use to solve this given question of continuity. Now limit extending to 0 plus f of x equals to limit extending to 0 plus 2x plus modulus x upon x equals to 2x plus x upon x equals to 3x upon x equals to 3. Similarly, limit extending to 0 minus f of x equals to limit extending to 0 minus 2x plus modulus x upon x is equal to 2x minus x upon x equals to x upon x equals to 1. Thus, limit extending to 0 plus f of x equals to 3 and limit extending to 0 minus f of x equals to 1 implies limit extending to 0 plus f of x not equal to limit extending to 0 minus f of x, implies f of x is discontinuous at x equals to 0. Hence proved. at what point f of x equals to 1 upon x minus 4 minus 5x is discontinuous. Solution: let f of x equals to 1 upon x minus 4 minus 5x equals to 1 minus 5x into x minus 4 upon x minus 4 equals to 1 minus 5x square plus 4 into 5x upon x minus 4 equals to 1 minus 5x square plus 20x upon x minus 4. Now numerator part can be p of x and denominator part that can be the q of x, that is p of x equals to 1 minus 5x square plus 20x and q of x equals to x minus 4. Therefore f of x equals to p of x upon q of x. Since f of x is equal to p of x upon q of x, that is, it is a rational function, that is f of x equals to p of x upon q of x, and if p of x and q of x are polynomial functions on R, then f of x is continuous at C if C is not root of q of x and q of C not equal to 0, then f of x is continuous. We conclude that a rational function is continuous at every real number for which we can define the function. If the function is defined, then it is continuous, but if q of x is not defined, then function is not continuous. Now here is a p of x equals to 1 minus 5x square plus 20x, which is a polynomial, quadratic polynomial, which will be continuous for all x belongs to R. So there is no doubt about numerator part, that is p of x. Now consider denominator part, q of x, that is x minus 4. Now q of x must be not equal to 0, that is x minus 4 should not be equal to 0, but for x equals to 4, the denominator becomes 0. That means the q of x is not defined. Q of x is not defined for x equals to 4, but q of x is defined for every other value, but q of x is not defined for x equals to 4. Therefore the only one point of discontinuity, that is x equals to 4. Therefore given f of x is discontinuous at x equals to 4. So x equals to 4 is the only one point for which f of x is discontinuous, and for every other value of x, f of x would be continuous. So that is what solution to this given question. At what point f of x equals to x plus 2 upon x square plus 6x plus 5 is discontinuous? Again the same, that is a given question is a rational function, and we can find out the point of discontinuity by equating denominator to 0 and finding out the values for which the denominator becomes 0. Let f of x equals to x plus 2 upon x square plus 6x plus 5. Let p of x equals to x plus 2 and q of x equals to x square plus 6x plus 5. Now given rational function is not defined if q of x equals to 0. That means for what values of x f of x is not defined, that we can find out easily by equating denominator to 0. So equating denominator to 0, that is x square plus 6x plus 5 equals to 0. Now we will find out the factors. Now after getting the factors, we get x equals to minus 5 and we get x equals to minus 1. Therefore, f of x is not defined if x equals to minus 5 and x equals to minus 1, and f of x is defined for every other value of x but not defined for x equals to minus 5 and x equals to minus 1. Therefore, points of discontinuity are x equals to minus 5 and x equals to minus 1. Define f of 3 in a way that extend f of x equals to x square plus 2x minus 15 upon x minus 3 to be continuous at x equals to 3. Solution: f of x equals to x square plus 2x minus 15 upon x minus 3. It is a rational function, and where p of x equals to x square plus 2x minus 15 and q of x equals to x minus 3. Therefore, f of x equals to p of x upon q of x, and this rational function such that q of x must not be equal to 0. Now we will find out factors of numerator and denominator, and we also find out is there any common factor in numerator and denominator getting cancelled. If they are cancelled, then given rational function gets simplified. As per as the given question, f of x is continuous at x equals to 3 implies limit x tending to 3 plus f of x equals to limit x tending to 3 minus f of x equals to f of 3, and we require to find out the value of f of 3 equals to how much. The function is already continuous at x equals to 3. Therefore, limit x tending to 3 f of x equals to limit x tending to 3 x plus 5 equals to 3 plus 5 equals to 8. Now, limit x tending to 3 f of x equals to f of 3. Here 3 stand for 3 plus as well as 3 minus, both the result would be the same. So f of 3 equals to limit extending to 3 f of x. This result is nothing but equals to 8. Therefore f of 3 equals to 8. This is required solution of the given question. Discuss the continuity of the function f of x equals to tan inverse x upon x for x not equal to 0 and f of x equals to 1 for x equals to 0. Solution: since f of x equals to tan inverse x upon x for x is not equal to 0 implies limit x tending to 0 f of x equals to limit x tending to 0 tan inverse x upon x. To find the limit of this function, we use L'Hospital rule, that is limit x tending to 0, derivative of tan inverse x is 1 upon 1 plus x square and derivative of x equals to 1. Therefore, it becomes limit x tending to 0 1 upon 1 plus x square. Applying limit, we do get 1 upon 1 plus 0 square equals to 1 upon 1 equals to 1. Therefore, limit x tending to 0 f of x is equals to 1. Let us call it equation number 1. Since as per as the given problem, f of x equals to 1 at x is equal to 0 implies f of 0 equals to 1. Let us call it equation number 2. From equation 1 and 2, we observe limit x tending to 0 f of x equals to 1, and this is what we have the equation number 1, and f of 0 equals to 1. Since limit x tending to 0 f of x equals to f of 0, which is nothing but condition for continuity of a function. Since both the results of equation 1 and equation 2 are equal, therefore we say that given function f of x is continuous at x equals to 0. Hence the result. Find the value of alpha and beta if the function is continuous in -3, 3 where f of x equals to 3x plus alpha, x is greater than -3 and less than 0, and for x greater than equal to 0 less than 2 the function is 3x plus 2, and f of x equals to beta plus x for x is greater than or equal to 2 less than 3. We need to find alpha and beta values given the function is continuous in -3 to 3. Now logic behind solving this question is, from the first two equation, from first equation we do get limit x tending to 0 minus f of x equals to limit x tending to 0 minus 3x plus alpha, and from the second equation we get limit x tending to 0 plus f of x equals to limit x tending to 0 plus 3x plus 2. The function is already continuous at x equals to 0. Therefore, to find alpha value, I am going to use the relation limit x tending to 0 f of x equals to limit x tending to 0 plus f of x. And after that, to find out the beta value, the logic is, from this second equation I do get limit x tending to 2 minus f of x equals to equals to limit extending to 2 minus 3x plus 2. And from the last equation I do get limit extending to 2 plus f of x equals to limit extending to 2 plus beta plus x. So this is the logic, and the function is already continuous at x equals to 2. Therefore limit extending to 2 minus f of x equals to limit extending to 2 plus. By equating this, I can easily find out beta value. Now let us do the problem in detail. Step 1. Limit extending to 0 minus f of x equals to limit extending to 0 minus 3x plus alpha. Applying limit 3 into 0 plus alpha equals to alpha. Therefore limit extending to 0 minus f of x equals to alpha. Call it equation 1. From equation, limit extending to 0 plus f of x equals to limit extending to 0 plus 3x plus 2. Applying limits 3 into 0 plus 2 equals to 2. Therefore limit extending to 0 plus f of x equals to 2. Call it as equation number 2. Since function is already continuous at x equals to 0, therefore limit extending to 0 minus f of x equals to limit extending to 0 plus f of x. Now writing their respective results from equation 1 and 2, we do get alpha equals to 2. So we got first result, alpha equals to 2. Now we are left with beta. Under the step 2, limit extending to 2 minus f of x equals to limit extending to 2 minus 3x plus 2 equals to 3 into 2 plus 2 equals to 8. Now limit extending to 2 plus f of x equals to limit extending to 2 plus beta plus x equals to beta plus 2. Call it as equation number 3 and call it as equation number 4. Since the function is already continuous at x equals to 2, implies limit extending to 2 minus f of x equals to limit extending to 2 plus f of x, implies 8 equals to beta plus 2, implies beta equals to 8 minus 2 equal to 6. Therefore beta equals to 6. Hence we got alpha value and beta value. Hence the result.